Hello, 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 organic chemistry. Welcome back. I am really excited to continue our stereocenters. Okay, when we looked at our history video, which is number 1, this is number 2. So if you are watching this video first, you want to stop and take a look at that history video first. There was just an awful lot of information in there. I just wanted us to get a feel for the fact that this actually started as a mystery and has evolved over the last 250 years. So the good news is that we've learned a lot in the last 250 years. The bad news is that means the vocab can be just a little bit confusing. So I want to continue that history, but in this video, I want to apply it. That way we get some idea of why we even care about that 250 plus years of studying our compounds and our organic compounds. So let's kind of group our history in 3 different regions and 3 different groupings. So that first set in the early to mid 1800s, we had a good 50, 60 years there of studying organic compounds. This is what really kicked all of this off. And what's awesome is that this whole study we mentioned in the last video really started in an awesome place. We started with wine on that one. So if you're taking and you're a super curious chemist or physicist and you love to drink your wine, naturally you'd want to study that wine. And what happened was they took those crystals that were left behind in the barrels, in those wine barrels, and they were curious and they started to monkey with them. And what was noticed in that 50 to 60 years was really 2 huge areas. The first one was that these crystals, some of our organic compounds, rotate light. That's pretty awesome. Okay, and then the theory out of that was that you had to have something without symmetry in your solution of whatever compounds you're looking at in order to rotate light. So there was this element of asymmetry that has to be present. Both of these are still concepts that are used today. And what's awesome, let me take a minute and talk about the rotating light, and then we're going to hit the asymmetry. So with the rotating light, in 2020, we still use polarimetry. It is a way to look at these organic compounds and sometimes tell this is one of the properties that's actually different with these compounds. So how does that actually work? Well, I took just a little snippet here from Wikipedia, and I referred to this Wikipedia right here. So how does that work? They took polarized light and really 5-second synopsis of polarized light. When you pass light through a polarizer or something that can polarize light, what happens is you take all those different directions of light. Light is traveling as a wave in all kinds of directions. And when you pass it through something that can polarize light, what's happening is you're just letting the light that can oscillate in a certain plane through. So you're letting light that is only oscillating in one plane through. And this light we can pass through an organic sample. And what's really crazy is then that light rotates. So I love this Wikipedia diagram right here. What they're doing is taking light, passing it through some sort of prism or a lens and polarizing that light, and they're getting just that one plane with their light, and then they're passing it literally through an organic sample. So when they first started these studies, that would have been wine and tartaric acid. And then check it out. If literally we're oscillating nice and vertical here, look what just happened to the light after it passed through that organic sample. That light just rotated, either clockwise or counterclockwise. So this is an instrument. This is a polarimeter. we have them in our lab. So polarimetry comes from those ideas in the early 1800s, and it's still used today. We can put organic samples into a polarimeter, and not only will it tell you if your sample rotated light, it will tell you how much. So that's pretty awesome. So a whole bunch of language is coming out of this strange phenomenon in the early 1800s that we still see today. So to give you some idea, when you look up a compound, you're going to see out in front of its name, let's look at epinephrine. If you look at an EpiPen, you might see a plus out in front of the name, or a minus, or a little L, or a little D. All of these are referring back to rotating light. Which direction is light being rotated? So you can look up compounds today. Shoot, go look up Ritalin on Wikipedia and see if you see a plus or a minus in there. You will see all kinds of vocab with that. So the first thing is that we've known for 200 years is this rotating light. So that's pretty crazy. And then we're going to add to that idea in just a second with our Pasteur. But then we also have this connectivity to asymmetry. Well, what in the heck does that even mean? And where did that come from? So really out of that 50 or 60 years came two really important ideas that we're going to spend a little bit of time with. The first one is that how do you have asymmetry in organic compounds? Your sp3 tetrahedral, if we have 4 different groups attached, we have asymmetry. So that's our first job. We're going to take that and apply it. And then second, why do we care about the rotating light, and what did Pasteur discover? It turns out with organic stereoisomers, okay, this is our modern day term, with our different compounds that rotate light different, it turns out that they only have 2 properties that are different. So what is so important for that 1800s that is carried through today? There are only 2 properties that are different in these compounds. If we're looking at rotating light is number 1. So those crystals from tartaric acid, when Pasteur literally separated those crystals with the tweezers, one set of crystals rotated light in one direction, the other set of crystals rotated in the other direction. But if you were to check something like melt temp, boiling point, physical color, properties, all of those physical properties, they would all be the same. There is a second property that Pasteur discovered that is different, and it is phenomenal, and it's why these things are so important to us, and that is biological interactions, or I'm going to call it biological activity. So this is why we spend an entire section on our isomers and our configurational isomers, which is what these are and where we're headed, because literally, if you just had 2 of these compounds mixed in a dish, you wouldn't be able to tell them apart. They would have only 2 different properties, and that is how they rotate light and how they interact in biology, which is really phenomenal. So of these 2, this is where we're going to head. All right, so how do we tackle this, and what are we looking at? Well, first of all, we need to spot where you can even have this asymmetry happen. So the first part of applying any of these ideas is something I'm going to call that we need to identify our stereo centers. Now let's highlight stereocenters. That's our modern term. And then I'm going to give you a list of all of our other terms. So what are we going to look for? We're going to start looking at our structures. And the first thing we're going to do always is identify where we might have this phenomena. Where do we have a stereocenter? So we're going to look for sp3 carbons. And we're going to look for 4 different things attached. So a lot of these studies started with wine. So let's take a look at, similar to tartaric acid is lactic acid. So let's start there. And that is right here. Let's look at that basic structure. Are there any sp3 carbons in this structure that have 4 different things attached to it? Yes, right here. Okay, that carbon is sp3. Okay, why not this carbon? It's not sp3, that's sp2. Okay, and then what's attached to it? Let's highlight and let's see if we've got 4 different colors. We have an oxygen. We have a methyl. We have a carboxylic acid. And then what is missing in our drawing is our hydrogen. I'll put that out in yellow. So right there, you have an sp3 carbon right there with 1, 2, 3, 4 different things on it. Okay, now our vocab is several names for this. Let's start old and get modern. Old might be an asymmetric center. Okay, that is a carbon that has no symmetry. You've got 4 different things on it. There's no symmetry there. And then as we grow into our next section, into Lord Kelvin and Fisher, and we look at things and issues of chirality, these are often called chiral centers. Again, a little bit older, but still newer than an asymmetric center. And then we can look at chiral, sometimes called chiral carbons. Okay, and then as of the 1980s to 1990s, the modern term for that carbon is called a stereocenter. I love it. So let's take a minute and let's go through the rest of these compounds and let's call them stereocenters and let's identify them. And the reason I wanted to give you the rest of this vocab is you will see it interchanged all over the place. But the modern and the newest in the last 30 years, we're going to go ahead and call it a stereocenter. So let's see if we can identify a stereocenter in the next 2 compounds here and here. These are classic. Okay, these studies started with the tartaric acids in wine and they moved rapidly into sugars and amino acids. So I'm going to give us a sugar and an amino acid and let's see if we have stereocenters in there and maybe we have more than one. So in any amino acid, let's check out this carbon right here. It's sp3. It has 1, 2, 3, 4 groups. That is a stereocenter. All of our amino acids, with the exception of glycine, have a stereocenter. And remember, our 2 things that we learned in the early 1800s is that they have different biological activity. So if you have a stereocenter in your body, you prefer one of those arrangements in space versus the other one, which is pretty crazy. Okay, our sugars, then let's take a look at it. Do we have any stereocenters in our sugars? Let's go through our sp3s and see if we have any. Let's start up here. Here's an sp3 carbon. We have 1, 2, we have 2 hydrogens on there. Okay, that is not 4 different groups, so that is not a stereocenter. Okay, let me erase so I don't go too crazy there. What about this one then? Is this an sp3 carbon with 3 different things? Yes. We're attached to an oxygen. We're attached to a hydrogen. We're attached to another carbon and another carbon, except these carbons are different. They are not the same. We're going to do something called follow our path and see that they are not the same. You can tell from our Kekulé drawing, look at this carbon, it's attached to all this stuff. This carbon isn't. So that is a stereocenter on our sugar. So let's go ahead and mark it. This is one. Okay, let's follow the same logic. Is this a stereocenter? Yes. In fact, all 4 of these are stereocenters. They are all different, have 4 different groups on there. It is possible to have more than one stereocenter. What about just our alkanes? Is it only amino acids and sugars? Oh, heck no. In the 1800s to early 1900s, this was a huge area of study, thus the Fisher projections in the late 1800s to early 1900s. But our alkanes can also have stereocenters. Check out this carbon. We have an ethyl, a methyl, an isopropyl, and a hydrogen. There's your 4 groups. So that is a stereocenter. Do we have any other stereocenters in there other than this one? No. Like this one is a trick. It is not a stereocenter because you've got 2 of the same groups. You've got 2 methyls. So the only stereocenter in that one is that middle carbon. Okay, as we go through history, we hit the 1950s to 1960s and we started looking at drugs. We talked about thalidomide. This is the general structure of thalidomide. Do we have a stereocenter in thalidomide? Okay, well, all of these carbons are sp2. All of these are sp2. Here we've got some sp3 carbons, but they have 2 hydrogens on them. What about this one? This carbon has 4 different things on it. So that is a stereocenter. If you follow this way and this way, they don't look the same. This is a nitrogen, and then of course we have a hydrogen. So we have a stereocenter right there for thalidomide. Okay, we can get even sassier and start to ID all kinds of things in nature that prefer one stereoisomer over another. Here for funsies is cocaine. Can we spot, this is the free base of cocaine. Can we spot sp3 carbons in here that have 4 different groups on them? Yes, we have 4. So if you want to pause for a second, see if you can identify all 4. We've got 1 here, 1 here, 1 here, and 1 here. Now those aren't always easy to see because as you work your way this way, don't they look the same? But as you keep going, they get different. That is asymmetry. If we had a plane of symmetry there, it wouldn't be the same. We would end up not having a stereocenter. And then we talked very briefly about things like steroids. Steroids in your body all have stereocenters and lots of rings. So can we spot the stereocenters in here? Honestly, if you can spot these, you can do anything. Let's start with the straightforward one. How about this one? This one? And those. There are 5, and this is an estradiol. So in estradiol, you've got 5 stereocenters. All of those are sp3 carbons with different groups attached to them. So you want to stop and just pause and get used to choosing those. We kind of started with a nice, easy example and ended with a really mean example. So you want to practice those, that's for sure. And then as we kind of go through our history, So in the early 1800s, they had that nice philosophy of sp3 carbon in 4 different groups and having no symmetry. That stays true. I love it. So then starting in the early 1900s with Kelvin and Fisher, we started to add to that the idea of chirality and mirror images. So maybe those crystals that Pasteur was looking at, what if they're actually mirror images of each other? So now, if we picture these compounds as mirror images, then one mirror image rotates light in one direction, the other rotates light in the other direction. And now this is where the term chirality is coming from Lord Kelvin. He's picturing this like a right hand and a left hand. So you'll see an awful lot of vocab that refers to chirality in mirror images. The only way we can have these stereoisomers that behave in this way is if they're actually mirror images. So I want to take a real compound and give perspective. Let's add to this picture a little bit. This is limonene. Okay, now remember there's only 2 things that are going to be different with these compounds. Number 1, they are going to rotate light different. Now the way I've drawn these, we actually have the mirror images. And number 2, they're going to interact in biological ways different. So I really want to give perspective to this. Let's take limonene. Limonene has been around forever. It has been studied almost as much as tartaric acid for this phenomenon. Okay, let's just group together what we would know by the early to mid 1900s. Number 1, one of them smells like mint and one of them smells like orange. So let's put perspective. These are the same compound. They are just flipped over. These are the same. But these is a mirror. So in other words, these 2 compounds are mirror images. So one mirror image smells like mint. One mirror image smells like orange. This is what I mean by biological activity. Your smell centers are biological. They are very shape related. They recognize different shapes. The only thing different with these compounds is the fact that they're mirror images. They would have the same boiling point, the same melting point, the same color, everything. So you can see why this has been a huge mystery for 200 years. If you have a mixture of these, you could never really separate them. How in the world could you tell one from the other? Well, you could definitely smell them. So one mirror image smells like mint, the other one smells like orange. Awesome. That's our biological activity. I'm going to put smell in here. And then it turns out that if you can get your hands on the one that smells like mint, it will rotate light counterclockwise. And the orange one will rotate light clockwise. Okay, awesome. So if you look up limonene, you will find all over the place a little plus or a D in front of the name. The little plus, again, is our rotating light. So for rotating light clockwise, this is our mint. It is rotating light clockwise. And then if you were versed in your Fisher projections, you could draw the D. Okay, now that D is a little bit old. We're going to refresh that in just a second. Okay, so both of these, this is awesome. We just got a little bit deeper. And what's phenomenal is that we've got something that you can test really easily. Does it smell like mint or does it smell like orange? They're not all that simple, but for this one, for limonene, it is, which is why it's quite famous. And they both rotate light different. Okay, so now we're on a roll. We're in the early 1900s. This is awesome. Let's take a second. Let's find our stereo center. It is right here. Okay, this is our stereo center. And these are mirror images of each other. But now here's where the caveat comes, and here's where the last 50 years of stereo center research is. And here's the deal. Which one is which? Okay, our mint and our orange is our biological activity. Our rotating light, clockwise or counterclockwise, neither one of these gives us structure. So what if you're picturing our thalidomide story? Let's go back up here. Thalidomide has a stereo center right here. That means it has a mirror image. You have two mirror images with thalidomide. One caused severe birth defects. One, I'm going to just say SD for severe birth defects. And then number two, one of them alleviated nausea. So this would be awesome, except now it gets phenomenally important which one is which, doesn't it? And the only way to truly tell which one is which is by its structure. What makes this mirror image is its arrangement in space. So if one of them's going to cure cancer and the other one's going to kill somebody, don't you need to know which one is which? You need to know the arrangement in space. So as of the 1960s to 70s, this is where we're headed. We are going to figure out which one actually looks which way in space. So this is the point of the 1966 Prologue Kohn-Ingold rules. And we still use these today. We are going to up the ante. We are going to identify and assign our stereo centers. Now, as of 2020, the only way you get absolute configuration, that means the absolute knowledge of which atoms are which atoms in space, is through X-ray crystallography. So if you're ever asked, how do you determine literally that shape in space, it is absolute configuration can only come from X-ray crystallography. So now let's identify and then assign our stereo centers. So I'm going to just do the two that are close to each other. These two are mirror images. And then how do you assign RNS? RNS is the only system that is going to tell us our 3D arrangement in space. So let's get all modern and let's just apply the rest of the video. What do we have here? We have mirror images, modern term, enantiomers. Okay, the compounds themselves are enantiomers. We only compare two at a time, and we are comparing these two. Okay, this carbon is a stereo center. When we identify and assign, we treat each stereo center different. All right, let's assign. Let me show you how to do that. We're going to start with our drawing. And I'm going to redraw this first one. We've identified our stereo center. And just hold your seats. We're going to bust out our model set. We're going to need a Newman projection. Okay, so I found my carbon, and it has 4 different groups, and I've got a hydrogen that's missing. Okay, how do you actually give an arrangement in space? How do you assign RNS, and then what do you do with it? Well, we're going to go through a series of rules. So number 1, we just ID'd our stereo center, and I typically put a little star on there. Number 2, we are going to do what's called rank your groups. And how do we rank our groups? There are 2, let's put them under ranking, okay? Number 1, atomic number. And number 2, we're going to follow our path to the first point of difference. So when we're looking at a stereocenter like this, we have to literally trace out and follow our path. So I want to teach us how to do that. This is not an easy example, so we're going to come back to it. So let's start with these rules on a nice example first, and then we're going to come back and assign our limonene and figure out which one is orange and which one is mint. All right, so number one, start by identifying your stereocenter. Let's start here. We've got a nice sp3 carbon with 4 different things on it. Number two, we are going to look at what's attached, and we're going to rank. Let's start with atomic number. Okay, that's the easier one. So let's start there. Let's look at atomic number. As I take my stereocenter, everything is based on that stereocenter. So start there and follow your path out. What do you hit? I hit a bromine, an oxygen, a carbon, and a hydrogen. So since all 4 are different, I need to rank all 4 of those atoms. In this case, atomic number totally works because they're all 4 different atoms. So bromine would be number 1, oxygen's number 2, carbon's number 3, and hydrogen is number 4. And we are going, our highest ranking is our highest atomic number. So we're going to mark bromine as number 1, oxygen is number 2, our carbon is number 3, and our hydrogen is number 4. Okay, then that's part number 1. Okay, we've identified, we've done our ranking. Now number 3, wait for it. Newman projection. We're going to put this on a Newman projection, and we are only going to look at half a one because you're going to put your stereocenter right there, and your Newman projection will always be your stereocenter to number 4. So put number 4 behind you. And if I then, let me give myself some space with my Newman projection. If I then take my Newman projection and I take this model and I match them, bromine is up here on number 1. OH is down there. My methane or my methyl group is right there. And number 4 kind of disappears. This is my stereocenter. So what do we do with the ranking then? Put in your ranking and literally connect your numbers. If you are, so let's call that number 4. You're going to connect that ranking. So if you rotate clockwise, that is R. If you rotate counterclockwise, that is S. This is the only unambiguous way to show structure and 3D arrangement of stereocenters. We will always use R and S. It is the only unambiguous way. It is what has been in practice for the last 50 years. So even though you may see all those other terms, plus, minus, LD, all of them can be ambiguous. This is the only unambiguous way to assign that stereocenter. So what would this one be then? Well, we're going clockwise, so that's R. Okay, so then I drew the other one. How do you get the mirror image? 2 of them are swapped. So in fact, our mirror images, if you build your model set, hit pause and use your model set to build these, you're going to find that you cannot superimpose. Just like your hands, you cannot lay them on top of each other and have them line up. When you put your hands together, you're looking at the mirror image. When you try to lay them one over the top, your thumbs are on the wrong side. It is the same for these compounds. If you keep 2 the same and you swap 2, we should get the enantiomer. So let's put our ranking in. Okay, here's number 4. Here's number 1, number 2, and number 3. Okay, but here's the trick. What would we do with our Newman projection? What does this Newman projection look like? Remember, your stereocenter has to look down number 4. So you have to switch it. So hit pause on the video and build this on your model set. If bromine is up here and number 4 is behind you or away from you, then you're going to notice that your OH ends up here. They have just been switched. So now let's put in our ranking. Holy crap, let's connect them. We are going counterclockwise. That is the S. Okay, now we're going to practice this in class. Let's do a couple more, and then we'll see how long our video is looking. Let's try this one. We've got that stereocenter and lactic acid. You see the difference between this and the beginning of our video. This one has bolds and dashes. How are we going to rank this one? Well, we're going to follow our path out and hit oxygen. Follow our path here and hit hydrogen. Oh, we hit carbon. And carbon. Okay, not all 4 have to be different on the first path, but we can still rank. Our hydrogen is number 4 and our oxygen is number 1. We just don't know our 2 carbons yet. So I'm going to go ahead and put in the 4 and put in the 1. And then let's follow out again. This is what our second ranking. Number 1 is atomic number. Let's write that better. Number 2 is follow your path. This is what follow your path means. Right now you're hitting carbon and carbon and it looks the same. So let's follow your path out again. This carbon is attached to 3 hydrogens. This carbon is attached to 3 oxygens. Oxygen wins. So our ranking then becomes, let's give ourselves some space here. 1, 4, 2, 3. Let's put that in a Newman projection. That OH is number 1. Our number 2 is that acid. Number 3 is that methyl. So let's assign that stereocenter. 1, 2, 3. And that is counterclockwise. So that would be S. Okay, now I love this example because this hits the most common mistake on assigning RNS. It is not total atomic number. It is the first atom you hit. Because if you were to picture and add up your molecular weight for carboxylic acid, you would want to rank that number 1. That's not what you do. You follow your path to the first atom you hit. And you start there. And then you follow your path out to the second round of atoms you hit. So that's why our OH ranks higher than that big carboxylic acid. It's not about the weight. You hit the oxygen first. Okay. So then what do we do for our amino acids? Let's do a ranking on this amino acid and try that. Here's our stereocenter. We hit nitrogen, hydrogen, carbon, carbon. So with all of our amino acids, they're exactly like that lactic acid. Hydrogen's number 4, nitrogen would be number 1, and then we would have 2 and 3 for that carboxylic acid. So then what does your gut tell you? This one would be, hit pause. Let's try that on our model set, and this would be an S. Okay, how do you follow your path when you've got a bunch of carbons in a ring? Well, let's identify our stereocenter. I'm going to go ahead and add in my hydrogen. And then check this out. Now we're starting to get really sassy. Carbon, hydrogen, carbon, carbon. So the only thing we can tell is number 4. Okay, now we follow our path again. I'm going to color code. Carbon, hydrogen, hydrogen, carbon, carbon, hydrogen. So right away, this is a point of difference. And then what about this third one? That methyl is all three. Let me give myself some space. I'll write it out here. All three hydrogens. So all three of these are actually different. We're the most carbon wins on this one. So this is going to be number 1, number 2, and number 3. So if you put that on your Newman projection, you are looking at 1, 2, 3. How in the world did I screw that up? Sorry. You are looking at 1, 2, 3. Okay, let's connect our numbers. That is an S. Okay, let's get one little bit sassier and let's connect these. Okay, so here's my stereo center. Looks kind of similar, but this time my hydrogen is out in front. And now I've got a competition right here with 2 carbons and 2 carbons. Okay, double bond is going to win. So how are we going to then rank this one? Well, we've got a number 1 to this side, number 2 to this side, number 3 to this side. Now I'm going to show you a trick and then we'll call it a day on this video. Let's take our Newman projection, except remember we saw earlier that if number 4 is out in front, we're going to have to invert everything. So you'll notice that these are going to have to switch in order for number 4 to be in the back. So now here's our number 2, number 1, number 3, and this is R. All right, let's hit stop on this video and take a second to do some of these practice. I have left you 2 sassy ones, so go ahead and hit pause on this thing, and then we'll pick up with these and hit video number 3 and just practice.